Today I'm going to give a brief update on this LED curtain that I previously built based on some feedback from some of you out there. But primarily this video is going to be about this. And that is a wearable battery-powered LED matrix. In my case, I put it on a t-shirt. Now note that this matrix can be synced to your LED curtain or any of your other WLED controllers, but it can also operate independently. I'm going to talk about the LEDs, the battery, expected battery life, and how I put it all together. I'll also cover how you can use this when you're not connected to Wi-Fi. So hang around. Hi, and welcome to Resin Chem Tech. Today I'm going to give step-by-step instructions for how I built this battery-powered wearable LED matrix that you can sync to other WLED controllers like I have it synced here. Now, as always, be sure to check the video description. Down there you can also find a written guide to this project that includes step-by-step instructions, wiring diagrams, parts lists, and more. But before I actually get into the t-shirt, there are a couple of updates I want to give regarding the LED curtain that I received from some of the viewers out there. Now, in my original LED curtain video, I had actually socketed my ESP32 controller so I could swap out between standard WLED and sound reactive WLED, because standard WLED normally runs a version or so ahead and has some additional features but doesn't have sound reactivity. However, a YouTuber out there who goes by the handle of Brian Seahack, sorry if I'm mispronouncing your name, had recommended looking at something called WLED MoonModules. I'd never heard of it, but when I took a look, what it does is it is cutting edge. It takes the latest WLED standard version and merges in the latest sound reactivity features. If you want to know more about MoonModules, check out the link down in the video description. The only reason I'm mentioning it here is because I am going to use MoonModules on the Matrix t-shirt, so the configuration menu might look a little bit different, but rest assured everything I show will work just fine with standard WLED or sound reactive WLED. One other thing to be aware of, if you're thinking about putting MoonModules onto an existing WLED controller, is certain GPIO pins are reserved in MoonModules. In the case of my LED curtain, one of the GPIO pins I was using for my microphone was reserved in MoonModules. This required me to do just a little bit of rewiring to the controller to be able to use MoonModules. I do make a note of that in the original blog article on the LED curtain. Another recommendation came from YouTuber JD Wiso, if I'm saying your name right. Once again, I apologize if I'm not. And he mentioned using something called xLights with the WLED curtain. Now, if you're not familiar with xLights, it's generally used for those large outdoor Christmas displays that are synced to music that you may have seen around your neighborhood or elsewhere. I'm not an xLights user. I've played with it just a little bit, so please don't ask me questions about xLights. There are plenty of tutorials and other online videos out there about how to use it. The important part here is it now does offer native support for WLED. So WLED is a listed vendor, so that makes it possible to integrate your WLED matrix into xLights and use xLights for more advanced animations and things like synchronization to music. Okay, let's move on to building the actual t-shirt, and what I want to talk about first are the actual LEDs themselves and take a look at the power draw to try to get an idea of the kind of battery power we're going to need and the battery life we might expect. For our t-shirt project, we're going to use these even smaller fairy lights. Now, I'm using these smaller ones for a couple of reasons. For one, it's going to allow me to fit more LEDs in a smaller space. And I'm also hoping that they're going to draw significantly less power because we want this project to actually be battery operated. But very similar to the LEDs that we used for the curtain, you'll notice that these have the same spacing of about 4 inches between pixels. And also, just like our LEDs for the curtains, these are WS2812B, and they come in the same density. It's a little bit misleading here, but they show 2 strings in a package of 5 meters each, but there are a total of 100 LEDs. So it's still 100 LEDs per 10 meters, just like with the LEDs we used for the curtain. So before I even get to the design stage, there are a few things that I want to test here that I'll need to know. For one, I want to know what the total maximum amp draw could be from 100 of these fairy lights. I couldn't find an actual spec on those, so I want to know what the maximum amp draw is. That's going to impact a few things. For one, how long our battery pack might last. And secondly, it will affect the design of the controller, whether I feel safe running the amps through something like the Electro Cookie board, or whether I would need to do like I normally do and split off 5 volts to run directly to the LEDs. I also want to check voltage drop. So I want to see here these last few pixels at the end of my 100 LED string, whether these are fading or having any kind of issues that might require me to figure out how to do power injection as well. So I've created an exact replica of a standard WLED controller here. We're going to use this little USB digital tester to measure our amps. I've had to create my own couple of little USB connectors here because I'm going to actually use a 10 amp power supply for this test. Now, there's no way this is going to draw 10 amps, but I do want to know what the maximum amp draw can be, and I don't want that limited by the power supply. So I'm going to start out by using a 10 amp power supply to power the whole thing. But there is one other thing I want to test before I hook all this up. So what I want to double check before I actually do my test is I want to check the voltage output of my power supply. That's always a good idea to do. And I also want to make sure I didn't do something stupid like reverse polarity when I made my USB connectors or set up my breadboard. So I've removed all the components. And first I'm going to test my power supply output. And I'm getting 5.21. Now this meter does tend to read about a tenth high. So I'm getting somewhere around 5.1, 5.2 volts. And if I come down here and I check my breadboard down here, you'll see I'm still getting exactly the same thing. So I don't have any kind of significant voltage drop anywhere. And just to check my polarity, if I had it backwards, I would be seeing a negative voltage. So everything is good in terms of polarity, and I've got good output from the power supply. Yeah, I put all my components back, and I've got everything hooked up, including our USB tester here. Hopefully you'll be able to see that. I'm going to go ahead and plug this in. And you see our LEDs did light up. Now I did go ahead and go into WLED and tell it that I had 100 LEDs here. So let's go ahead and turn on WLED. And we can see right now with the 100 LEDs lit at about 50% brightness on orange, I'm drawing about 470 milliamps. Let's just turn off the LEDs and see what the controller by itself is going to draw. So that's going to be around 170 milliamps, give or take. So even if the lights are turned off, as long as the controller is powered, it's still going to be drawing about 170 milliamps. Let's turn these lights back on. Let's go over to white and let's go to full brightness. I also have the brightness limiter disabled in WLED to make sure it's not going to be limiting the brightness. And remember, we have a 10 amp power supply. But here on full bright white, we're right at 1 amp. So 100 of these fairy lights with the controller is going to draw right about 1 amp. But we're generally not going to run that bright, and we're normally not going to run a solid white color. So let's just pull up just a couple of effects here, choose a couple of other colors. This happens to be the chase effect, and at 50% brightness, about 440 milliamps. So I think as a general rule, what you're going to see here is that most of these effects are going to be around 500 milliamps or less. That's going to vary a little bit. Some of them may be as, yeah, there we go, as low as 260, 250 milliamps. So that gives us a good handle to know we're never going to pull more than 1 amp. But in most cases, for most of our effects around 50% brightness, we're going to be somewhere in the 250 to 500 milliamp range. We should also check for voltage drop here. So these are the pixels at the very end of the strip. And the good news is I'm not really seeing any fading or at least no shifting of color. They might be just the slightest bit dimmer here at the very end, but at least they're not going towards pink or red. So that's a good sign. That means we can power the 100 LEDs without needing to worry about power injection, which is going to be very beneficial for my planned design. But with that, now we know the total amp draw, and we also know about power injection, so we can move on to figuring out how we're going to actually build this thing and how long it's going to run off of a battery. Now, before I move on to the next step of actually attaching the LEDs to the t-shirt, let me state this right up front. Crafting and sewing and working with fabrics is not my forte. I'm sure there are better ways to do this that might make the wiring look a little bit neater. In my case, I plan on wearing this t-shirt along with my WLED curtain on Halloween night to greet the trick-or-treaters. So when it's completely dark, the wiring isn't nearly as noticeable as it is under bright light or daylight. But I'm sure that there are other ways to do this that would be much better than the way that I show. So use what I'm showing here kind of as a proof of concept or a guide for your own way of doing it, not necessarily a step-by-step process, as I really didn't know how I was going to do this when I went into it. But this is the approach I'm taking. I've laid out a 10 by 10 grid with pixel spacing of about 28 millimeters or 1.1 inch on center for each of these. I'll have 10 columns by 10 rows. So that's not going to be the exact same dimensions as the curtain, but I think it will look nice on this t-shirt having the nice square. A pixel will be sewn into place at each of these little marks that you probably can't see. Again, 28 millimeter on center spacing. Now, I think the biggest issue is going to be how to deal with this 4 inches of wire in between each of the pixels. But that's the approach I'm going to take and see if it works. After giving it just a bit more thought, I felt like this masking tape was going to be in the way of trying to apply my pixels. So what I've done is I've taken a silver Sharpie and I've went ahead and laid out where all of the pixels are going to be centered. And then I think what I'm going to try and do is I'm going to try to use a little bit of this fabric glue to hold, at least temporarily hold the pixels in place, then come back through and put a little bit of black thread around each side of the pixel to try to hold it in place. We're going to give this a shot, and that's the approach I'm going to take. So I've completed the first column here, and these have all been glued down with this fabric glue, which is actually working better than I expected. These do seem to be pretty secure. I did go ahead and add thread to the first couple of these, but to be honest, it's an extremely monotonous, time-consuming procedure. I may end up just going with glue and putting the thread at a few stress points, like here with the beginning of the strip. This is by far probably not the best method, but I would say, I guess, look at the concept and not necessarily the method that I'm using. I'm just hoping that maybe when it's dark and these are lit up, the wiring won't be too noticeable, and I'll try to manage the wiring as best as I can. But I'm also going to have to deal with the issue of this JST connector that connects my two strips together. The way it works out, this JST connector is actually going to end up being at the top of the shirt, and I'm not sure I'm really going to want this big old bulky thing there, so I'm going to have to figure that out. But I also figured I probably ought to test these as I go along to make sure I'm not causing any issues with bending these wires. And to do that, I would like to go ahead and be able to use my battery-powered controller. So I'm going to glue a few more of these down. I'm going to set the shirt aside to let it dry, build the controller, come back and be able to test these, and then finish off the shirt. Now the controller for this is just going to be a standard WLED controller, and I covered that in a lot of other videos, so I'm not going to go into a lot of detail here. But I am going to be using an ESP32, and the reason for that is I want to run the same firmware that's on the LED curtain, and that is running WLED MoonModules, and it has sound reactivity, so therefore it requires an ESP32. Now I'm not going to hook up a microphone to this. There's one already hooked up to the LED curtain. I'm also going to be using the SN74 AHCT125N logic level shifter. Two reasons for that. Primarily is because the same shifter I used with the LED curtain, and I want to try to keep things as consistent as possible. But mostly it's because of its smaller size. And the reason why is I'm going to try to squeeze everything onto this small electro cookie board. Now normally when using something like a Wemos D1 Mini and an I2C logic level shifter, it fits on this small board just fine. But the ESP32 is significantly bigger than the Wemos D1 Mini. So it's going to make things fairly tight, and there's no way to fit this I2C level shifter on here. Therefore, I'm going to go with this one. The reason I want to try to use this smaller board, if at all possible, is that normally whenever I use the ESP32, I step up to a board of this size, and that ends up meaning that I have a controller that is somewhere around this size. And since this is going to be portable, and it's actually going to be attached to my body, I want to try to use this smaller enclosure, and I've went ahead and 3D printed myself something that's going to attach to my belt, and then I can simply slide this controller in there and have it mounted on my hip. And for that reason, I'm also going to add a push button to this, just to give me a local way to turn off those lights and conserve a little battery if I want. But the challenge is going to be to see if I can get all of the wiring necessary for everything on this small little electro cookie board. So it took a little bit of creative wiring, but I did manage to squeeze everything onto this small electro cookie board. There wasn't room to actually mount the logic level shifter, so I actually cut off the extra length of pins and had to solder short wiring runs to it. And I put a little Captain tape underneath here just to make sure we don't have anything that comes into contact. But I was able to do this by running most of my wiring underneath and kind of creating a 5-volt rail and a ground rail out of one of each of the columns. So the good news is I should be able to fit this into that small 3D printed enclosure. And here is the complete controller inside of that smaller enclosure. Now once I determine final wiring links, I will come back and add a JST connector on this end that will connect to the LEDs, and this end will be connected to a USB-A that's going to plug into our power bank. I do want to make a note of the power to the LEDs, because in most of my videos I say that you should not run the power for your LEDs through your controller board. But if you recall from when we measured the amp draw of the system, the maximum on full bright white was 1 amp, but most of the time we are running around 500 milliamps or less, and about 170 milliamps of that is just the controller itself. So in this particular case, I feel okay with running the power for the LEDs through the electro cookie board. But for anything that has much higher amps than this, you would want to run a separate 5-volt lead to your LED strip. And speaking of power, I'm going to be using this 10,000 milliamp hour battery pack, drawing around 500 milliamps. I should get somewhere, give or take, around 20 hours of continuous use. Even on full bright white, it would still give me a full 10 hours of use off of a fully charged battery pack. And this will fit nicely into my pocket. So you might be wondering, could you power this system off of something like AA alkaline batteries? Well, probably. If you take 3 alkaline batteries in series, you're going to get about 4.5 volts. That's probably enough to power the system, but alkaline batteries normally only have a milliamp hour rating of somewhere around 1800, 2700 milliamp hours. In a perfect world, that means you should get somewhere between 3.5 and 5.5 hours battery life. In actuality, you're probably only going to get 2 to 4 hours of battery life. So while you might be able to use batteries, a better option is probably something like a power bank. And to get an idea of the runtime, take the milliamp hours of that power bank and simply divide that by the 500 that we estimated as the average use for the system. And that'll give you an idea of how long you would get off of a single charge. Now with this build, it gives us an easy way to test. So it's time to go back to the t-shirt. I finished 2 columns here, and after letting this dry overnight, this fabric glue is actually doing a pretty good job at holding this on here. I am glad I decided to put a piece of cardboard underneath here because the glue does soak through a little bit and stick some to the cardboard, but it pops loose pretty easy. But just keep that in mind if you decide to follow my crazy design here. At this point, it's time to do a sanity check. I want to check to make sure we haven't damaged the LEDs, and this will also be the first check of my wired controller, and we're actually going to power this off the battery pack. So I'm going to plug this in. And the good news is we do have a light there, and all of our LEDs light up. So that lets me know that A, my controller is working, we are actually running off of battery here, and all of the LEDs are working. So now it's a matter to continue running these columns, and I still have to figure out what I'm going to do here with this big JST connector where the 2 strips come together. After watching a number of YouTube videos that show how to actually repair a broken wire with these fairy lights, I've made the decision I'm going to go ahead and cut off my JST connectors and solder my 2 strings directly together. Now, what I believe one challenge was going to be was after I cut off the JST connectors was keeping track of which wire was which. With the JST connector, I'm assuming that the 5-volt line is being indicated by the red on the connector. But unlike our WS2812B pixel strips, where every pixel indicates the ground, data, and 5-volt line and also indicates the data direction, once I cut off those JST connectors, I needed to make sure that I kept the wiring correct in terms of both polarity and data flow. When I looked a little bit closer at these pixels, I did notice, and it's a little bit hard to see here, there's a colored dot on each of these individual pixels, and they alternate red, green, red, green, red, green, all the way along the strip. Now, initially I thought, great, the red is indicating our 5-volt line, and the green's either indicating either the data or the ground. It really doesn't matter as long as I could indicate one of these outside wires. But when I actually started pulling these apart and tracing them, if you look here, this is our red on our JST connector, which I would assume would be our 5-volt line, but our red dot is over here on the opposite side. What's more, if you trace along these outside wires where I've pulled them apart, here's the green dot. So the red is connected to the green, connected to the next red, and so on. I couldn't find anything other than this picture that was on the actual Amazon listing to describe exactly what these red and green dots mean. But I think from best I can tell, it's indicating where the data is coming in and data is going out. So here at the green dot, we see our data in, assuming this is the center line, is connected next to this outside wire. Over here, we have the data going out next to this wire. So I'm guessing that the red and the green indicate data in and data out, and they're always connected along this outside wire, which is opposite of the 5-volt wire. And that's good enough to be able to keep track of these wires when we cut and resolder them. So here's what I've decided to do as a test. And I should have done this before I started gluing some of the pixels down to the shirt, but that's water under the bridge. So I've ordered another set of fairy lights that I can use as a test. First, I've made sure that all of the pixels are working, and they are. So now what I'm going to do is I'm going to unplug the power from these, and I'm simply going to cut 2 pixels here off of the end. Okay. Now I'm going to see if I can solder these back together and still have these 2 pixels light up. Before I can solder these back together, the first thing I have to do is remove the thin layer of clear insulation that's on each wire. Now obviously these wires are insulated, otherwise you would be getting shorts all over the place as these wires are touching each other. Now the wires are obviously way too small to try to use anything like wire strippers, but one of the methods I've seen used most is a small piece of sandpaper. You can simply take the end of your wire here and gently scrape off the insulation. And you're going to need to do this probably multiple times. And the question is how do you know when you actually have enough insulation stripped off? I've seen other methods that use either a flame or a soldering iron, but I want to somewhat control how much insulation I'm removing. I don't want it to remove all the way back and melt, because I'm going to need to re-insulate these wires to make sure that they don't short out when they come back together. One way I've found that you can tell pretty easily, as you strip off the insulation, you'll start to see a little bit of copper color come through, and that is the actual wire itself. So just continue stripping these off until you feel like you've got bare copper exposed. You probably can't see it here, but I can see a little bit of copper color there, and you also notice that the shine is off the wire, and that should be enough to allow us to make an electrical connection. Another way I can check to see if I've got enough insulation removed is I can try a continuity test between the end of this wire and the end of the wire coming out of the JST connector. And you see I do have continuity there, so I am making good electrical contact. Now that will work fine for your 5-volt and your ground line, but it won't work for the data line because signal isn't flowing through when these things are not powered on. But at least gives you an idea of whether you've got enough insulation removed or not. All right, I've stripped the insulation off of all 6 ends here. I was able to test continuity on the outside ends of both strands. I've made sure I've got my dots lined up, green to red, and I've just twisted these wires together, which I don't really like doing. I really prefer to solder my wire connections together, but these wires are so thin that they're going to conduct heat really quickly, and I'm afraid it's going to melt off that insulation. So we're going to plug in the power here with them just twisted together at the moment to see if our process worked, and it didn't. So I've got something here that doesn't have a good connection, so we're going to have to drop back and try it again, but that's why I tested before I put this shrink wrap into place. Okay, I took them back apart. I did some more sanding, and this time I actually did add just a little bit of heat. I used an aim flame just on the very tip of the wire just for a second or two, and then did some more sanding after that, and I got much better looking bare copper and obviously a much better connection here. I do think I'm going to come back and try to put just a very little touch of solder on the very ends of each of these. I don't want to apply much heat again to melt the insulation, but just a little dab of solder on the very tips of each of these to make sure that they hold together. Then I'll put the heat shrink back on and give it one final test. Okay, we have success. I did add just a little touch of solder on the ends of these and put my heat shrink on there. And you can see that everything seems to be fine. I'm not getting any shorting when the wires touch, so I don't have any exposed wiring left out here. Everything looks good, and I think this is the method I'm going to use on the t-shirt. Still not ideal, but it's definitely better than having the big old JST connectors sticking up right underneath my chin. Okay, I used that same exact technique to cut the JST connectors off and connect these 2 strips directly together. And again, I've got no shorts and no problems with connectivity. But at this point, the 2 strips are joined together and I can continue gluing my LEDs all the rest of the way. Now, the technique I used here was to glue down 3 or 4 pixels at a time, weight them down with a little bit of, I just used wire spools here, and give them about 15-20 minutes to dry before moving on. Otherwise, I found that I kept popping the previous pixels loose when I'd try to bend the wire for the next set. The most important thing here is to try to keep your pixels vertically and horizontally aligned and equally spaced. That's going to give you the best appearance for the matrix, regardless of how the wiring looks here, and I'm sure there are better ways to do this.
Finally, all 100 pixels are now glued into place, and it's time to give this one final test. So again, we can see all 100 LEDs are lit up. Let me bring these lights down just a little bit. Bring the brightness down just a tad on the LEDs. And let's just check a couple of things here. Make sure it looks like our matrix effects are working, and they do appear to be. So at this point, it's a matter of giving the LEDs a good 24 hours to dry. Then I will take the cardboard out of this, probably clean up a few of the wiring runs here as best as I can, and maybe add a little bit of thread to things that might appear to be something like stress points, like maybe my join here and the tail end of the strip. At least all 100 LEDs are on, and they are all working.
So what I want to first check out before I actually put this on and show you how it can be worn and moved around and work without Wi-Fi is I want to test out the sync between the LED curtain and the matrix t-shirt. Now, just in the interest of time, I'm not going to go into the details here about how to set up syncing in WLED. I do cover that step by step in my blog on how I set it up for my LED curtain and my t-shirt, and there's also information on the WLED website. Just know that in my case, I'm setting this up so any changes I make to the curtain are synced over to the t-shirt in terms of effects and colors. I could make the t-shirt update the curtain, or I could actually set it up two ways, but I'm just setting up a one-way sync between the curtain and the t-shirt. I'm going to come over here, I'm going to turn the lights down just a little bit. Let's start out by just powering on the t-shirt. Okay, now I've got the sync set on both of these to on, so they should be syncing together. So I'm just going to run a quick little playlist here that's going to test a few different things. So we see our colors are staying in sync. This is just solid patterns, so checking out the colors there. Now we're going to run some effects, and again, the effects are just being controlled by the playlist on the LED curtain, but they're being synced over to the t-shirt. So all that looks good. Things are pretty much staying in sync. And the one thing I am curious about is the scrolling text. Interested to see whether t-shirt has enough density of pixels to actually be able to read the text. So let's take a look at that. And as you can see there, it actually looks pretty good. You can definitely read the text on the t-shirt. And again, they're staying in sync with each other. Let's just throw up a different color here. Now, the one thing I can do if I want is I can turn off the sync on these two devices. If I do that, the t-shirt is now able to simply operate independently of the curtain. So I can do whatever I want over here separately with the t-shirt, while the curtain continues to do its own thing. If I want to sync them back up again, I just turn on the sync options. And now whenever I change something on the curtain, it once again will sync over to the t-shirt. So the sync works really well. Again, I can control them independently. I can control them together. I could sync from the t-shirt to the curtain, from the curtain to the t-shirt, or actually both at the same time. So any change made on one will be reflected on the other. Hey, just a quick look here at the final controller. Now that I've determined the wire length, put some braided sleeves on these. Once again, this is going to go onto my belt. Controller will simply slide into that. This end with the JST connector obviously is going to go and plug into the start of the LEDs on the t-shirt. And the other end, I've got a USB that is going to plug into my power bank. And the idea is the power bank will simply go into the back pocket. So the last thing I want to cover is how you can use and control your wearable LED display when you're not connected to Wi-Fi. There are a few changes you may wish to consider regarding your WLED controller setup. Once again, in the interest of time, I'm not going to cover the step-by-step process of configuring the access point for WLED. I do talk about some best practices in the written blog article, and of course you can find more information about this on the WLED website as well. But there are some changes you may want to make if you're going to routinely be using your wearable outside of your Wi-Fi network. All right, so what I want to do now is I want to test this both on our local Wi-Fi and as I move out of Wi-Fi. So I'm going to go ahead and turn this on. Again, I'm here in my own driveway, so I am connected to Wi-Fi. And if we look here again, we've got a number of different effects. Everything is controllable through the phone at this point. But now what I'm going to do is we're going to start walking down the street until we leave Wi-Fi. Okay, this is just about the edge of my Wi-Fi zone, so we're going to keep on walking out. And what I want to show here is as I leave the Wi-Fi area, the shirt's going to continue to run the last effect. So whatever effect it was running when I was in Wi-Fi is going to continue to work and run as I leave Wi-Fi. So at this point, I should definitely no longer be connected to my Wi-Fi. Okay, so now I've actually moved almost a block away from the house, so I'm definitely out of the Wi-Fi zone. But what has happened is now the WLED controller has started broadcasting the local access point. I've now joined that local access point, and by going to the controls, once again, you see I have complete control of the t-shirt. And I can simply use my phone to change to whatever effects that I want to run, and it works fine, and I could continue to walk around the neighborhood. As soon as I move back into my local Wi-Fi, once again, this will reconnect to my local Wi-Fi. I'll switch back to Wi-Fi on my phone and be back right into normal operation. Okay, so now I've returned back to the house. The WLED controller has joined back onto my local Wi-Fi. So I once again simply just put my phone back on the Wi-Fi, and once again you see that I now have the ability to run all the effects and control the t-shirt, whether I'm on Wi-Fi or whether I'm down the street or away from home, via the local access point being broadcast by the WLED controller. And naturally, just after I finished recording and editing this video, Quindor over Intermittent Tech released a video about a potentially better way to use your WLED controller when you're not on your own local Wi-Fi. In his case, he flips it around. Instead of using the access point from the WLED controller and joining your phone to that, he uses the phone as a hotspot and then joins the WLED controller to your phone. That way your phone maintains internet and cellular connectivity. If you're interested in his method, I'll leave a link to his video down in the video description. Thanks, Quindor. So that's going to do it for what is once again a very long video, but I'm trying to put this out a little bit early to maybe give you some time to think about how you might add wearable LEDs to your Halloween costume for this year, or even the Halloween costume for your kids. And one last reminder to be sure to check the video description for more information, including a link to a written guide that has step-by-step instructions, wiring diagrams, parts list, and more. If you saw anything in this video you liked, do me a favor, hit that thumbs up button. That lets me know I'm on the right track with these videos. And if you'd like to see more of my content, click that subscribe button and ding the little bell icon if you want to be notified when I release new videos. And as always, I'd like to say thank you for watching, and I hope to see you soon.